Hello, everyone. I am going to be talking about RF fundamentals today. So let's start with a quick look at what we're going to be talking about. So this week, we're going to be looking at frequencies in the RF spectrum, some modulation and channel access techniques, antennas and EM wave losses, cable connectors and losses, the idea of mismatch and max power transfer, and finally, what is a dB? So RF is an extremely broad topic and can cover everything from basic ham radio communication up to 5G cellular communication. I see it used in everything from RF plasma generation for semiconductor etching, all the way to metamaterials used in bodies of stealth planes, where they're actually reducing radar cross section to make the plane look kind of RF invisible. So very broad topic. We only have an hour today, so I'm just going to lightly touch on multiple topics across RF. And these topics are really going to help just give you a basic understanding of fundamentals used in RF systems. But I strongly encourage everyone to continue a personal study of these topics and just keep pushing your knowledge. So let's get started with a quick look at the RF spectrum. Now, when we're thinking RF, we're thinking radio frequency, and this is referring to electrical energy all the way from 3 kilohertz up to 300 gigahertz. So some common frequencies we're going to be familiar with are like those used in our AM radios, FM radios, so around the kilohertz region up into around 100 megahertz. Everything in our 4G cellular communication, and now including 5G, where we're actually going all the way up into 28 and around 40 gigahertz. Some of the LMR bands for land mobile radio span across from around 100 megahertz all the way up to almost 900 megahertz. And then there's a lot of frequencies also used throughout ISM, which actually stands for Industrial, Scientific, and Medical. And you'll see that again, that's the type of stuff being used in semiconductor manufacturing or MRI machines, inductive welding type of manufacturing. So just quickly off to the right here, you'll see we've got a few things I want to bring up. So when we're saying AM, FM, we're talking amplitude frequency modulation. I hear a lot of folks talk when they're saying 4G or 5G, thinking that the G stands for gigahertz, actually stands for generation. LMR is referring to land mobile radio. And then as I mentioned, ISM is referring to industrial, scientific, medical fields. And as we're going through the first part here, semiconductor folks, don't get too discouraged. I'm going to bring up some pieces involving the RF plasma a little bit later on towards the end. So let's get started with looking at the idea of what is frequency. So when we're thinking frequency, we're talking cycles per second, and this unit is typically displayed as hertz. So when we're thinking in terms of time, we're going to be referring to period, and we're going to be looking at the time it takes to complete one cycle, one sinusoidal cycle. And then we're thinking distance, we're looking wavelength. So this is going to be the physical distance that one of these sinusoidal cycles would span to complete. So up here as an example, I have a 2 megahertz frequency where we're just going to do a quick calculation. So for example, if we're calculating period, we're doing 1 over the frequency. And so 1 over 2 times 10 to the 6, and we're looking about 0.5 microseconds to complete one of these cycles. Now, in terms of wavelength, we're actually using the speed of light in the calculation, and we get a result of 150 meters, so very large physical distance. Now, when I'm referring to period, we're usually thinking topics like signal timing, or that's going to come into play in modulation. Or wavelength, we're referring more to antennas and EM structures where a lot of these factors will play into how they perform there. So let's take a quick look at some common types of RF modulation. Now, we're using modulation because it's not going to do us a whole lot of good if we're just having a plain RF signal. We're not going to be able to encoding any information. So there's a few techniques that we can do. We're going to look at a few more simple cases, but in the case of analog modulation, we have amplitude modulation, frequency, and then phase modulation. And this is where we're actually encoding the information from the signal that we're trying to transmit in variations of amplitude or variations in frequency, or even variations in the phase of these signals. Now, as we move towards a more complex system where we're trying to transmit a lot of information, especially very rapidly, we're going to use things like digital modulation. So now, instead of encoding the analog signal in a waveform, now we're actually encoding zeros and ones. And we can do this in a few ways, quite a few ways. Here I have an example of where we're actually manipulating the amplitude and frequency and phase to indicate zeros and ones. And so this can get a lot more complex as we move into more sophisticated digital modulation schemes, but it's just good to get a rough idea of how we are going to encode that information. And when we're thinking from something that's going to be a more a simple type of modulation all the way to a more complex, what comes to mind for me are those more simplistic, something like an audio signal we're going to be encoding using AM or FM. This can be in something you'll see like ham radio or even radio broadcast, all the way up to extremely complex digital modulation techniques like used in 4G LTE, where they're using something called orthogonal frequency duplex multi-access. So it gets pretty complex pretty fast, but I just wanted to use this just as a reference. So along with that idea of OFDM and what we're doing in a digital communication system, you know, we're not always just broadcasting wide out into the open and hoping for someone to pick up a signal. Usually we're having multiple communication channels, and when we have different users, we have to have ways to make sure that I apologize, I'm having some difficulties here with my microphone today.
Yeah,
so
no, Steve, you're fine. You don't go out. You're fine.
Okay. So when we are dividing this information among the users, I have a couple examples here. One is for time division, and one we're actually dividing the channels by frequency. So we have either time division or frequency division multiple access, and there's several other methods we can use to split up information between users. And an example of some of these, like TDMA, is going to be for LMR mototurbo, or FDMA for LMR P25 phase 1. Now, when it comes to the ISM applications, typically they're only requiring a more simplistic sinusoid. So this is where we can utilize just a continuous wave type of function, or maybe we're going to do some pulsing with that continuous wave. And the idea of this is, in these ISM applications, we're typically concerned with delivering energy to the target rather than transferring information. So, you know, for example, you know, in your household microwave, we're not trying to transmit some fancy signal. We're just trying to deliver the energy to heat up the molecules in the food. But these simple signals still can be useful in communication, where you might be doing something like CW keying and in transmitting like a Morse code. Now, if we want to get these signals from A to B, we're going to take advantage of the magic of antennas. And I don't know if a lot of you folks have spent much time looking at antennas, but the structure is usually very sensitive to physical size, and it's going to have a lot to do with how we're lining up the current distribution along the dimensions of the body of the antenna. And like here, we have an example of a quarter wave or of a half wave dipole, and we're actually observing we have that half wavelength of the frequency lining up across the body of the antenna. This is where I was talking about those wavelength, comes up when we're talking about these EM structures. And this is going to launch a wave, an electromagnetic wave out into space, where we're actually going to have this traveling through space with the electric field and the magnetic field perpendicular to one another. And when we're thinking these antennas in our system, the antenna selection can play a large role on the system performance. So you might have something where you're trying to cover a lot of directions and a lot of space, and you're going to use a omnidirectional type of antenna. So you're going to have more of like a donut shaped radiation pattern, versus if you're doing something that's going to be more point to point, you're going to want something that comes in a more directive type of pattern. So just as a rough example, a typical omni antenna, you're going to see gain of around 0 to 5 dBi. dBi is gain with respect to an isotropic radiator. We'll talk about this a little bit more towards the end of the presentation. As compared to something like a Yagi style antenna, which is a more directional antenna, you're going to see 5 to 12 dBi gain. And the more directional, we're talking higher gain in that particular direction. So we're going to get a lot less, out of the back. And when we're thinking antenna patterns, we can also think about how our antennas are going to be affected by their immediate surroundings. So typically, as antennas decrease in size, the efficiency is going to go down, but we can make use of ground planes. And so, for example, something like this, where we have a rubber ducky mounted on the top of a vehicle, and we can use this to help make the antenna look larger and increase the efficiency. And we're actually going to be able to have the energy radiating off of it like it was all sort of one piece. Now, so as the EM wave is going to be launched off the antenna, we're going to run into some other effects that are just going to occur to a lower signal at the receiver. So first one to consider is inverse square law. So as the signal radiates away, we're actually having a decaying effect over distance. And this is due to the idea of as the radiation expands, it's actually the same amount of energy is being distributed over a wider and wider area. And then we're looking at effects like the attenuation as the EM wave is going to travel through trees and plants and other vegetation, or even on a day where there might be a lot of moisture in the air, maybe there's snow or it's raining, we're going to get attenuation from the EM wave experiencing loss through the droplets. And then in a non-line of sight type of application, we're going to be looking at effects like refraction, where the radio wave is actually refracting off of things like mountains and hills and buildings. And again, we're going to experience that idea of inverse square law, where we're going to have the signal spread out again. And there will also be some losses experienced due to the surface that it's conducting on as it's refracting. And then even in something like a multipath environment, where you're going to have two waves that might be interacting at the receiver, they can come together and actually cancel each other out, and you'll have a smaller signal level at the receiver. So we've taken a moment to look at losses in more of like the EM wave out in space, let's take a moment to look at some of the losses in our system. So when we're thinking losses in the system, there's a few that come to mind right away. I'm thinking skin effect, some of the different limitations of cables and connectors, and then how these pieces are going to play into impedance mismatch. So starting with skin effect, the idea here is as the frequency is increasing, the current is conducting closer and closer to the surface. And so here's an example here to the left where at DC frequency, or at DC, so no frequency, you're going to have the current distribution spread out throughout the cross section. As we go maybe around 60 hertz, like it's coming out of the wall, you're going to see the current distribution move closer and closer to the surface, and where by time we're getting to our higher RF frequencies, it's going to be significantly existing close to the surface. And this means we're going to have less space to push all those electrons down the line. So you're going to have more electrons bumping into each other, and you're going to be experiencing more heat. And this, we can see that effect is getting worse as we go up in frequency. Now, some things you'll see is, for example, if you had a solid conductor going down your line and you're thinking, okay, current's conducting on the outside portion of the conductor. There's also, the consideration of, there's a lot of braided cable or, where there's multiple stranded cable. And so in the case of something like that, as the electrons are traveling down the line, they're actually going to be traveling on the surface of these individual threads. And so you'll see people take advantage of that skin effect in applications like that. A lot of times the consideration here is just the idea of more flexibility out of your cable. Now, cable and connector impedance, we're thinking there, I'm looking at the idea of coaxial construction of the cable or the connector. And so if we think about the breakdown of a coaxial cable, we have an inner conductor, a dielectric, a shield, and then an outer insulator. And the relationship between this inner conductor and this outer conductor, as well as the dielectric material that's in between them, is going to be a huge, or is really the deciding factor in what the characteristic impedance of the cable / connector ends up being. And when I'm saying characteristic impedance of the cable, I'm referring to this is independent of length or distance. This is just the way that actual configuration between outer and inner diameter and that dielectric, how that actually forms the impedance. So, and this idea is going to hold, similarly for connectors, just as it does for cables. Now, a lot of times we're thinking of RF cables being, lossy, or you're experiencing some loss as the signal's traveling down the line. Now, when we have we have a distributed equivalent circuit model where we're really going to be talking about the idea of capacitance, inductance, and resistance that you're experiencing down the line. So we can calculate these parameters, and we're going to set them up. Usually you'll see something like capacitance per foot, inductance per foot. But where this model really can be found interesting is as we are thinking about the way that the cable is experiencing loss over distance is, we do have some of that energy that's being converted to heat. It's just being lost due to the imperfectness of the conductor, or the fact that we have this capacitance here. There's going to be small amounts of current that are actually going through, or small amounts of energy that are actually being lost that's traveling from the inner conductor to the outer conductor. And so most are very low loss. We're usually not considering this as a huge factor, but as you get into more extended runs, it can get to be a little more lossy. And also an important thing I wanted to bring up is the idea of cutoff frequency. And this is really the idea of that inductance and capacitance relationship and how that's going to factor in as you approach higher and higher frequencies where the cable itself, just that inductance and capacitance, they're going to play into things that are going to make it a lot harder for that to look like a nice 50 ohm environment for the cable. And so now we're typically when we're thinking cables, we're thinking 50 ohms, and I want to take a look at that a little bit closer. Why are we always saying everything 50 ohms? So when we're referring to 50 ohms, this is really the trade-off between attenuation and power handling of these different system components. So 50 ohms is usually the standard you're going to see. You'll run into some other systems that are 75 ohm or 300 ohm. This is typically going to be dealing around Cat5 cabling, which is going to be used in your commercial like cable television systems. So now that we've started to talk about the idea of impedance, let's think, when are we usually hearing impedance? So we're usually hearing impedance when we're looking at the specs for cables, connectors, generators, output of transmitters, maybe a dummy load we're trying to terminate our generator into, or of antennas. And I see a lot of the folks on the communication side of things not really considering it too much because you get the system components, everything is typically rated for 50 ohms. You're not worrying about a lot of strange impedances happening. But the more that we understand impedance, and it's going to give us a more complete picture of our system and why we might be getting little reflections, especially when we're considering accuracy and efficiency of our system. So in order to start our exploration of impedance, let's take a quick look at Ohm's law. And Ohm's law, we're describing the relationship between power, voltage, current, and resistance. And impedance is really the AC term for resistance. So when we look at our primary items that we're interested in, usually we're trying to figure out how much power is being delivered to our load, or we're looking at what is the impedance of our system components. So in DC, this can all be done with So this can all be done with voltage and current. Now in AC circuits, we're going to be looking at the cosine of theta, which is actually the phase angle that's going to be between the voltage and current. And so when we're calculating the impedance here, we're going to be looking into the complex portions. And when I say complex, I'm saying that in AC circuits, your impedance is going to have a real and imaginary part. And this is going to be describing the relationship between that voltage and current. And the reason that we're getting these variations happening is due to these capacitance and inductive components that are playing in that are going to be shifting the phase around a little bit in our circuits. And here to the right, you see I've got this, it's a plot of the imaginary and real axes. And this is how we're describing impedance and using the real portion and a reactive portion. So when we're talking about complex impedance and we're thinking inductors, capacitors, we're looking at reactance. So here we have the equation for reactance of an inductor, and here we have the equation for reactance of a capacitor. So this is particularly important because when we're doing things like impedance matching and trying to get max power delivered to our load, we're going to be trying to keep this down closer to the real axis and cancel out these phase effects that are going to be happening along the imaginary axes. And so we can even see here that idea of the cosine theta. This is actually describing that relationship between the real and imaginary portions of the impedance. So now that we've been discussing impedance a little bit, let's take a moment to reflect on the impedance of the different components in our systems. So when we're thinking cables and connectors, we got a good look that there's a big capacitive and inductive component to them with a fairly small real resistance, because we're trying to get the signal to the antenna or wherever we might be going. We're not trying to burn it up as energy. Then we're looking at antennas. Again, it's going to be inductive or capacitive with a small real resistance. Plasma chambers, depending on what you're working with, it can look like a big capacitor or an inductor, or even like an inductive welding tool. Again, it's going to look like a big coil inductor with smaller real resistances. The only time we're really thinking of trying to use a purely real resistance is when we're using a dummy load and we're trying to just terminate all that energy and convert it into heat. And the idea of all these impedances is really coming into play when we're thinking of the idea of max power transfer. So the reason that we're asking for a certain amount of power from our load is because, and we're hoping to transmit all of that. We don't want to waste a bunch of energy in our system. So when we're doing max power transfer, this is the idea of the impedance of the source matching the impedance of the load. And again, in a lot of the RF systems you might be using, this is going to be pretty standard. You're connecting a 50 ohm transmitter into a 50 ohm antenna, but especially in the applications like on the semiconductor side where the load can look very non-50 ohm, there will be things like matching networks put into place. And even on different antenna circuits, a lot of times when guys are doing antenna design, they're trying to go to great lengths to match these complex impedances to make the load look like a 50 ohm. So you're transferring as much energy to the load as possible. Now, reasons why we might not be getting that full 50 ohms to our load or our antenna, it could be all kinds of different things. So some common reasons for mismatch that I see are different cable problems, like you have loose or intermittent connection, dense kinks and crimps, I apologize. I've been having some difficulties here with the headset today. So when we're talking different reasons for mismatch, we're thinking things like the crimping of cables. This is something you'll see, especially if you make too tight of a bend. You might get something like this. Now, this is with the insulation ripped away, but you could see the idea of if you overbent a cable and kinked it, that it could result in definitely a non-50 ohm type of impedance. Different things, over time, these connectors are going to be exposed to environmental factors, or cables are going to be exposed to different environmental factors. Can lead to things like corrosion and water intrusion, and the actual jacket getting a little bit funky and being hard to keep a good seal and protection of the outer conductors. So also we'll see this again, like improper bend radius if someone's trying to make a real tight turn. Connector problems. Here's a good example. Actually, someone had placed a cable into this input port, and the cable had some corrosion on it. Actually resulted in the leafing being a little bit spread out and getting damaged. So now you're approaching that no longer a nice 50 ohm connection. Now, things like antennas, you could have icing occurring on them or snow, and a lot of these will also have like a plastic protective housing. Over time, UV can damage those types of things and allow for cracks where water might get in. But definitely that idea of, if we're having another material sitting on this antenna, we're going to be getting no longer that nice impedance match or perfect impedance match like we had before. Or even if you're in the situation like where you're calibrating a transmitter or checking power, there's definitely cases where people are frying the dummy loads, or maybe it's in a tight space where it's overheating, or even using a load for the wrong range, and you'll see some charred resistors on the inside of these things like this, which are definitely no longer a 50 ohm. Now, the way we're typically quantifying these amounts of mismatch is using the quantities of VSWR and return loss. So this is what you'll commonly hear. So let's start by taking a look at VSWR. Now, VSWR is the ratio of the max amplitude of a standing wave to the minimum amplitude. So here you can see we've got our forward traveling wave in blue and our reflected wave in red. And in the case of like this, where if we were to have an open termination, maybe something happened where a cable wasn't completely connected, and you have all this energy reflecting back at the load, you're actually getting an extremely large standing wave occurring from the places along the line where these waves add together, and where they then you'll see these minimal points, these nodes, where they're actually subtracting perfectly. So let's take a quick look at some different VSWRs that I usually see in systems. So starting with that reference that we just looked at of complete reflection, where we're having these points along the line where we have a huge summation between the forward and reflected wave, and then other points where we're perfectly canceling. So here I've got this maximum minimum just to kind of show the difference that we're seeing in the variation of that standing wave. And also, just for note, the blue wave here is the forward wave and the yellow is the reflected. So a lot of times when we're calibrating systems, we're trying to keep our VSWR no more than 2 to 1. And so you can see here there is a fair amount of variation along the line here, and this can definitely lead to some additional inaccuracies in a measurement, versus something here where we're going to have what you'll usually see in dummy loads during these calibration processes is something worst case, usually like 1.5 to 1, and that's where you're going to see this is going to be a very minimal reflection, very minimal standing wave you're going to experience along your line, compared to something like a perfect match, which is at VSWR 1 to 1, where we literally have no variation along the line. There's really no VSWR. Now, return loss is another quantity you'll commonly see used to express this reflection. And again, this is describing the ratio of the reflected power measured at the input test port. So before we were looking at that voltage standing along the line, now we're thinking in terms of the power we're measuring back at the test port. So we're essentially describing the same quantity, and we can very easily move from one to the other. One thing that is very helpful to refer to is here where we actually have a return loss VSWR being translated into how much power is being reflected and how much power we're actually delivering to the load. So for example, once we get lower than about 10 dB of return loss, or that VSWR of less than 1.92, now we're getting to where at least 90% of the power is being delivered to the load. And then as we move down from there, we continue to have more and more power being effectively transferred to the load. So let's take a quick example of a VSWR return loss measurement of an antenna and of a cable. So a lot of our RF systems, we're not worried about measuring impedance directly to calculate our mismatch. These quantities of reflected power are fine with using VSWR and return loss. So for example, here we have an antenna where we are measuring with a cable analyzer, and we can see over the specified band of operation for this antenna, we were aiming for at least 1.5 VSWR or 14 dB return loss, which is only 4% of the energy reflected. We're actually getting at some of the most performant points, we're getting close to that VSWR of 1.02 or about 36 dB, which is only 0.01% of the energy reflected. So that'd be points like here and here around that 840 mark. Now, in terms of a cable, we're going to see, we're here, if I'm sweeping over, this was a cable I actually tested at my desk, just a short run. We can see if we're looking over 10 to 100 megahertz, or 1 to 100 megahertz, we're actually seeing, again, very, very low VSWR, very, very low return loss values. So we're getting, only 0.01% of the energy reflected back at the source. And this is using a little 50 ohm termination on the end of the cable just to approximate that perfect match. So what about in that non-perfect 50 ohm system? This is where I'm typically thinking a very dynamic load like a plasma chamber. This is definitely going to be anything but 50 ohms, where we're actually going to have to put impedance matching network between the generator and a capacitively coupled plasma or inductively coupled plasma. And here we're actually doing a measurement of voltage and current. So this was an experiment I'd actually done at a lab about a year ago, doing some test measurements with one of our products. And here you can see we're actually measuring the voltage, current, and phase over a very short, about 120 microsecond pulse. And with that value, like we were looking before when we were talking impedance, we can actually, observe the magnitude of the impedance, and we have the phase angle here. We've got the real portion and the imaginary portion. So the matching network ended up getting us fairly close to where we were seeing, approximately 60 ohms of the impedance magnitude. So it actually got us pretty close to getting a good impedance match. But you could see the real resistance was very low, only about 1.25 ohms, but the imaginary portion, being capacitive, was closer to minus 60, which was, when we were talking earlier, we were thinking the lower half of the imaginary is actually, the lower half is actually going to be the capacitive region, where the top half will be the inductive region. So before we wrap up, I wanted to bring up one often used but not always understood topic, and that's the dB. And when we're talking dB, we're saying decibel, or 1/10 of a bell. And this is a unit that the bell came about as being named in honor of Alexander Graham Bell. It's often used to express ratios of signal gain or loss, or even absolute quantities, such as dBm will often use to refer to power. Now, dB is usually very common in RF systems because we're dealing with very large, very small values, or large amounts of gain and loss over a system. And the way that the dB helps with that is because we're expressing these values logarithmically instead of in linear terms. So we can see what would otherwise be maybe very difficult calculations with these extreme numbers, or very hard to see plots. We can now easily graph those in a way that we can break down much more realistically. So we'll start off with dB as signal gain or loss. So we're thinking dB as signal gain loss. We're thinking we'll just use like this here. We've got a black box system where we're giving some input power and then we're going to receive an output power. So in terms of signal gain, maybe you have an amplifier where you're amplifying from a 10 watt to a 50 watt signal. That's going to result in about 7 dB of gain. Or in terms of signal loss, like maybe along a cable, say you put in 200 watts, but your resulting power is 150 watts. Now we're describing that as minus 1.24 dB. Now, as I was mentioning cables, you'll usually see a loss quantity of like dB per foot or dB per meter. Here's an excerpt I took from a data sheet of an RG393 cable, where you see we actually have dB per 100 feet as a measurement. You can see as we go up in frequency, those loss values are getting higher and higher. And so if we were to think of this in another way, at 10 megahertz, we're, for every 1 foot that the signal is traveling, we're only getting a loss of about 0.138% of the power. So in case of a 1,000 watt signal, this would be 1.38 watts per foot. Another way you'll see the dB described is signal power with respect to a milliwatt. So that's the M portion of the dBm. And so in the case of 0 dBm, that's 1 milliwatt. That's exactly the reference point. And then as we increase logarithmically, we're looking at 10 dBm, 10 milliwatts, 20 dBm, 100 milliwatts, and then that 30 dBm mark is where you're hitting a watt. Now some typical power levels I'm seeing in these different systems be like 1 kilowatt to 10 kilowatts. So that's where we're seeing that 60 dBm to about 70 dBm. Another way you'll see dB used is describing the ratio of a fundamental or carrier frequency to a harmonic, and this is being used as dBc. So the C in this term is referring to signal power with respect to the carrier. So this is actually an excerpt from one of the semiconductor generators I've seen, and you can see we have this spec harmonics dBc, spurious content dBc. So we're saying, what kind of signal levels with respect to the actual frequency of interest, which in this case is 1356, what kind of signal levels might we expect to see? Because we don't want all this spurious content. We don't want all these harmonics in here. We want the main frequency of interest. So in the case of like this generator here, that's outputting a max of 600 watts, we're saying, okay, all that other content is not going to be any larger than 60 milliwatts. And then earlier, I also mentioned dBi. So this is antenna gain with respect to an isotropic radiator. An isotropic radiator is going to be a great way to think of it is like a balloon. So if we were to have a radiation pattern that was going to spread evenly, almost like a perfect sphere, so it's spreading out evenly in all directions. That's a nice way to base some of our measurements, but really our real world antennas are going to be anything but a perfect radiation pattern, and we really don't want that. We kind of want to point the energy into our signal of interest. So in most real antennas, what you're going to see is the energy that would be otherwise this isotropic radiator being redistributed. So a good way to think of it is like taking that balloon and then sort of squeezing it in different ways. So you do have that same amount of energy that had been delivered to the antenna, but now you're rearranging how it's being distributed due to the antenna pattern. So something like this would be more like of our donut antenna pattern that we saw earlier, or something like this would be that directional antenna that we were looking at. So just to take a quick recap, today we were discussing frequencies in the RF spectrum. We looked at some modulation and channel access techniques, took a quick look at antennas and EM wave losses, got to look over cable connectors, losses and impedance, mismatch, max power transfer, and finally we got to take a look at a dB. And so, a lot of us might not be designing an RF transmitter or an antenna or a cable or connector, but I'm very sure that we're all using these in our systems. And the more that we understand these components, the more that's going to help us to effectively monitor our transmitted power, or maybe we're monitoring antenna VSWR, but this is really going to be a great way to get a health check of our system. And then also, if we're trying to do things like if we have a generator, for example, one of these ISM processes, or even if it's a comm system where you're just trying to increase efficiency, the more that we understand these ideas of mismatch and where these pieces might be coming from, or how impedance is being affected, can help us to get understanding of what things we can target to help reduce those reflections or these mismatches and increase the overall system efficiency. Now, these are several resources I personally have used that I think would be great for everyone to, if you want to do some additional learning and take a closer look at these different concepts. For one, you can always start with emailing us here at App Engineer, BirdRF. You're either going to get me or my colleague Greg, and we can help you out with, whatever RF concepts you might be trying to understand. There's a lot of other great resources out there, a lot of great documentation like Everything RF and Microwaves 101. And if you're feeling, where this is something that you want to actually try to do some of these simulations yourself, there's a great open source RF simulations software called Quite Universal Circuit Simulator. You can find that at the quacksourceforge.net website. This is really great, kind of like an open source version of Microwave Office. So really, really nice if you want to get a little more into it without having to spend any money on a big price tag simulation software.